Thank you very much. Yes, as said, my name's Tom Cronin. I'm special advisor. That's my title anyway. I'm not sure whether I'm the special or whether it's my advice that's special, but I'm a special advisor in the wind energy systems program within the wind energy department, or division as it's now called at Risø. Yeah, just very short. I was born in America, but I grew up and was educated in England, so I regard myself as an Englishman. And I've been working at Risø for about the last 6 years or so. And I hope that my knowledge and grasp of wind energy and power systems is better than my grasp of Danish. So I'm afraid I will do this in English and not in Danish. So just an overview of what I will talk about, a little bit about Risø and the wind energy division. Then a bit about the Faroe Islands study, which is the basis of this presentation. It's a study that we did a couple of years ago, looking at the possibilities for more wind energy in the Faroe Islands grid. And what we used was simulation software called Ipsos, and I'll talk a little bit about that. Some challenges that we had in modeling the system to make it suitable for simulations. Of course, what we're all interested in is how the model performed and what sort of results we got out. And some conclusions, and let's hope some implications for pumped storage. This work that we've done, it's been mentioned a couple of times yesterday, so I thought it would be good if, rather than just we all hear the results, we know a little bit more about the background and the work that went into it. Let's start with a little bit about Risø DTU. It is the National Laboratory for Sustainable Energy in Denmark. We now are part of the Danish Technical University, or I think it's the Technical University of Denmark officially in English, but it's abbreviated to DTU. A little over 2,000 scientific staff and 6,500 students. Risø itself is around about 650 staff, and this is we used to be called the Risø facility. We're now a campus, being part of a university by the Roskilde Fjord. We cover a whole range of research topics, mostly focused on sustainable energy. And of course, the ones that are interesting now are the wind energy and the Intelligent Energy Systems program. The Intelligent Energy Systems program is fairly new. They cover energy storage, electricity storage, autonomous grids, smart grids, distributed generation, all that sort of thing. So that's a bit about Risø DTU. Now let's move on to the Faroe Islands study itself. Indpasning af vindkraft på Færøerne. Commissioned by Yardfinchi. Is that anywhere near the correct pronunciation? Some nods, some shaking of heads. Okay, all know who I mean. And with some data from SEV, for which we're grateful for. The aims of the study were to investigate how well the power system on the Faroe Islands might cope with an increase of wind power, and to take a look at what the limitations are in this ability to take in more wind power. I have to say right from the start that pumped storage wasn't part of this study, but I hope that we will see that some of the results will give some interesting pointers as to where pumped storage might be able to come in. I said I'd say a little bit about the simulation software called Ipsos, which stands for Integrated Power System. It's one of those contractions which try and give a flavor of what it is whilst still being pronounceable. It's been developed in-house by Risø. this is marketing speak, a flexible framework for the simulation of multiple energy systems. And what that's trying to say is that it's been built so that particularly for systems that will have a number of different renewable energy sources coming into it. And whilst we fully admit that most of the things that we'll be looking at will be based around an electrical power system, that doesn't have to be the case. We can use any number of domains, as we call them. One might be an electrical domain, or a hydro domain, or a heat domain, or a mechanical energy domain. But the whole idea of it is that it's flexibility to accept different types of power sources. It's been developed with system performance simulations in mind, so it's not really looking at transients or dynamic behavior of generators or short circuits or anything like that. One of its strengths is that the supervisory and local controllers can be programmed as you wish. If you have a system which you want to operate in a certain way, so you have operators taking certain decisions at certain times based on certain parameters, then you can program that in as you wish. You're not limited to any particular box of control system at all. You're only limited by your ability to program. It does explicit modeling of the electrical networks, so there's power flow, both active and reactive power flow, load sharing between the generators, etc. The time steps between the calculations for the energy balance can be typically in the range of a few seconds to some minutes. In this particular study, I think it was 1 minute. And the simulation periods can be from hours to days, months, and up to years. And this is an important aspect when you're looking at renewable energy, as I'm sure most of you are aware. Because the renewable energy can fluctuate over the seasons, it's important that you take a long enough time span. Otherwise, if you focus in a too narrow area, you're likely to get results that are biased one way or the other. Very short, the Faroe Islands electricity system in 2006, this was the year that we had the data for. I won't go through it in detail because it's been covered a lot, except that as you all know, we have this mix of diesel and hydropower turbines, some wind. And we have this very nice profile that is very recognizable from a weekly and weekend pattern. So what does this model look like? Well, of course, what it really looks like is a bunch of computer code, but that's a bit boring to show. So conceptually, in generic terms, we can have wind turbines connected to buzz bars. We can have diesel generators, again, connected to buzz bars. We have some loads, and the all-important and interesting bit here is the hydropower. So we can have reservoirs that will flow into other reservoirs with or without turbines in between. Turbines at the end, we can model inflows and outflows. In other words, we can represent the whole of the hydro system. And if we translate that into the Faroe Islands simulation itself, this is what it might look like. As you can see, we have the diesel generators represented, we have the hydro generators represented, the reservoirs, the load on the Faroe Islands here, and some of the wind there. So that's the overall picture of what the model connections and components look like. Now, some of the modeling challenges, reservoir behavior. Now, I know some of you are going to be thinking, well, how can reservoir behavior be a modeling challenge? It's just a bowl of water, isn't it? Well, the thing is that because in our simulations we recalculate the energy balance of the whole system at each of the time steps. And in our case, that's every minute. We have to have suitable inputs for every minute. And one of the inputs is the inflow into the reservoirs. And that's a little bit difficult to measure unless we have a whole load of people with buckets trying to capture the water as it comes down the mountainside. So what we did was to try and take a period where we could see from the data we received that the turbines were not running, and take a look at how the level of the reservoir increased. And this can give you some kind of an average flow in, and you can check that if you have an adjacent period where the turbines do then run, then you can calculate the flow of water out because you know the load on the turbines and the characteristics of the turbines, so you know the water consumption. And if you then calculate with the water inflow that you have calculated, then you can see whether your simulated level of the reservoir matches with the actual measurements. And we were reasonably successful with that. Although I have to say it's still one of the uncertainties in our simulation. One of the other challenges we faced was how do we actually dispatch the generators in a similar way as to actually how it's done in real life. And the difficulty here is because this dispatching of generating units, in other words, the choosing of which generating units are going to make up the portfolio that covers the load in any one moment in time, it's done intuitively by the control room staff. It's a difficult job, but because they know their system well, they know their generators well, and they know the profile of the loads that's likely to come, they can handle this quite well. It's difficult to put that into a simulation, but we can see the preferences for dispatching the different types of generators and the different individual generators from the recorded data. In other words, we can see the time traces of all the generators, and you can take a look to see when certain generators are on together with others, and get a feel for what sort of combinations are common. And that's what we did to try and put into our controller. The hydro unit, their priority is fairly dependent on the reservoir level. That's reasonably straightforward. The wind power units are generally treated as unreliable. And yes, here is somebody from the Risø wind energy department saying that wind is unreliable. But what I actually mean by that really is that the generators that were chosen to fulfill a particular task in any one moment were chosen on the basis of the load that was on the system. We didn't take any regard of the wind power, so that if, as people are concerned, that the wind power suddenly falls out, then we still have the generation capacity there to cover the load. So we didn't do wind any favors there. And our algorithm for this unit commitment needs to satisfy some of the must-run units. In other words, for example, when certain diesels are started up, they must run for a certain time to preserve their lifetime. And these criteria are also fulfilled in the simulation. And then we fill up the rest of the capacity requirement according to the priority list that we generated.